So now we'll start the high energy physics session. So our first talk is from David Rousseau from Saclay. So he'll be talking about some new ideas for track reconstruction with ML.
Okay, so this is about using optical processing unit for tracking and calorimetry at the LHC. So hold on. So at the Large Hadron Collider, we collect proton collision, and we have a very high data rate, and the data is very complex. And for an event which is a record of a proton collision, we can see, spot muons, electrons, and then find the Higgs boson. But this processing is quite time-consuming, and we have more and more complex events and more events. So we're looking for new paradigms to process our events. So one of these new paradigms is machine learning, as we all know, and since a few years we do more and more machine learning. But there's a new device out there which we have explored the usage of, which is the OPU. OPU, like optical processing unit. So what is this? This is a very quite an amazing amazing thing, quite ingenious. This is made from say 2 parts. One part comes from standard beamer, well, high-end beamer, which is a laser shining on a matrix of micro mirrors. And with the position of the mirrors, you have basically an image with 0 and 1, which is then sent on the diffusive medium, say a layer of paint, and then you have a camera, regular camera, behind, which look at the image of the interference pattern. And what's going on in this diffusive medium is effectively a random matrix multiplication. This is a very large random matrix.
Transform.
If you want.
You can tune it and wrap it around.
Sorry, no, you cannot tune it. It's fixed by the device. Completely fixed by the device, the physical analog computation. And if you compute, it's by hand. It's typically the rate being 2 kilohertz. You have 10 to the 15 operations per second for a few watts. And a few additional feature is that any proximity neighboring information is completely lost. So 2 neighboring bits in the input are not more correlated in the output than the distance bits. And other thing is that what we get are called random features. They're all equivalent. So depending on what we want to do, we can take 10,000 of them, 100,000, up to 1 million, in fact. But they're all equivalent. And this is now fits into a shoebox in a standard rack in the computing center. And these are prototypes. Estimate price is 10 euro, not very fancy, but they are not yet on the market, and the company is just granting us access to these prototypes. Okay, tracking is the first use case. In short, it doesn't work, and see the longer presentation more about this. And for this shorter one, I concentrate on the calorimetry. So we've used a data set which was made by colleagues, who are exploring using deep neural nets to classify events from calorimeter information. So there are 3 types of simulated events: top pairs, WQCD, 3 channels: photons, charge tracks, and neutral hadrons, which are projected into a 2-dimension image, which is the one you see. So there are the 3 channels, one next to the other, and each channel it's basically the cylinder, which we have seen at the beginning, the cylinder which is cut open and put flat. And there are different granularity depending on where you are in the detector. So these are the images which we have to classify. To make a long story short, the longer story in the full talk, this is the image we fed in the OPU. We have to take into account the fact we have to quantize the image first. We have to make sure that there is a significant rate of bits which are set on. Otherwise, we have a lot of noise, and voila. the reference with which we are comparing is what is in the paper mentioned, which is a ROC curve on classifying top events compared to the others, and the curve which provides a meaningful comparison is this one, which is obtained by training a CNN and with the AUC of 0.91. The better other curves are using more complex architecture and more information as well. So this is what we want to compare to. And when we do the job, so from the random feature, we do ridge regression, which is basically multidimensional linear regression. So this is not really a training. This is just one simple linear algebra calculation. And you see the contours for the AUC according to the number of events used for the training or the calculation and the number of random features. And you see when we go for more than 20,000 of each, we get an AUC of above 0.9, so comparable to what we got with the CNN. Okay, so conclusion. So we have examined two use cases. So tracking didn't dealt with it. It's okay, no convincing results. Calorimetry, which is some kind of image processing, has performance in terms of AUC comparable to CNN. With 1 hour of processing and training, it's quite fast compared to the CNN mentioned in this paper, which is has required hours of days, of training. Although it's outperformed by more complex architecture. However, the inference speed is limited by the current OPU throughput, which is 2 kilohertz, while CNN inference, so CNN is a pain to train, but then once it's trained, it's super fast, and I put megahertz here as a guideline, but can be even faster. So it looks like this OPU could have, in fact, niche application for in the case where we need to retrain, since what is cheap is the retraining, in the case where we need to retrain often. And this is kind of a program which we want to do. And there is a draft paper, which is going to be finalized before the end of the year. And we want to thank people who have been supporting us at Lighton and people providing the datasets. Thank you.
Okay, thanks, David. So we hold our questions to the end. So why don't we go now to Gage. So Gage is from Princeton, and he will be talking about graph-based neural networks on FPGAs.
Hi, yes. Can you see the slides?
Yeah, go ahead.
Awesome. Okay. Yeah, thanks for the intro. So this work is concerned with tracking at the Large Hadron Collider. And the goal of tracking is basically to estimate the trajectories and momenta of charged particles in the innermost layers of the detector. So if you look at this top plot here, you can see a tracking event that is classified as high pileup, which means that there are a number of overlapping interactions here, producing a high number of tracks that need to be disentangled. And what we know, the LHC is tending towards higher and higher pileup during its lifetime. And we know that many aspects of current track building algorithms scale quadratically or worse with pileups. That, motivation number one is we need to develop some new algorithmic strategies to handle high pileup tracking. Also, the LHC produces an enormous amount of data that is filtered down by a trigger system. At the front line of the trigger system is the level 1 trigger, which is basically a specialized set of algorithms that run on dedicated hardware with sub-microsecond latency requirements. So motivation number 2 for accelerating some of our algorithms is to perhaps meet the latency requirements of the L1 trigger. So recent work has shown that graph neural networks are promising candidates for tracking applications. So at the left, I just wanted to, go over graph neural networks in general. You can see here for graph data, which is just a set of vertices connected by edges, a general message passing graph neural network will update the features of each vertex by essentially aggregating information from its neighbors. And you can see that here. We have a multi-layer perceptron aggregating information from the neighbors of a given node through some permutation invariant function. And then another multi-layer perceptron is used to ultimately update the state of the node in question. So, okay, with that said, how do we represent particle events as graphs? Well, so here's a kind of a cartoonish depiction of what's going on. But basically, you have here two hypothetical particles that run through and create orange hits in the detector. And what you would do is take those hits as a point cloud and connect them in some smart initial way, and then give that resulting graph to your graph neural network and ask it to classify the edges. So you'd want the green edges here would represent true edges belonging to a particle, and the red edges would be classified as false edges. So this is a edge classification problem. So in general, edge classifying graph neural network architectures, in a general sense, look like this. You have an input graph that might be encoded into some latent space, and then a graph module is run repeatedly on the encoded representation of the graph. And what a graph module is, it's based on an architecture called an interaction network, which basically has two multi-layer perceptrons in it. One is focused on updating the features of the nodes in the graph, so the hits in the detector, and one is focused on updating the edges in the graph. And after you've run the graph module a number of times, you then output at the end of the day edge weights that ideally give you some idea of the tracks in the event. And just note that we see very high edge classification accuracies for all of the architectures we're looking at. So we've accelerated these edge classifiers in two key ways. One of them is using the OpenCL hardware description language. And this study focuses on accelerating full event processing using a CPU plus FPGA coprocessor. So we used an energy cut as a proxy for graph size and performed a scalability study looking at the latency of the algorithms as a function of the event size. And saw that the FPGA implementation had a robust performance, achieving millisecond to second latencies for a wide range of graph sizes. Our second implementation uses HLS for ML, which is high-level synthesis for machine learning, a package that basically takes familiar machine learning code and translates it into machine-readable firmware code. So this study was performed using smaller graphs and an encoded representation of the interaction network. And so we did a physics performance study as a function of bit width, and then also studied the latency for small sectorized input graphs. And for these smaller graphs, saw latencies of ranging from 650 nanoseconds to about 1 microsecond expected. With that, thank you so much.
Thanks, Gage. So hold your questions, hold your applause. So our next talk is from Max. Max, are you there?
Hey, Phil. Yeah, can you hear me?
Yeah, I can hear you. So Max is from Triumph, and he will be talking about pion identification.
Awesome. You can see my slides?
Yeah, looks good.
Okay, great. So yeah, hi everyone. Thanks for the invitation. And yeah, I'll be talking about using deep learning for pion identification and calibration in the ATLAS experiment. So at Physics at LHC, we've already heard a little bit about this. We circulate protons in bunches around this 27-kilometer long ring. We collide the protons at 13 TeV, and we measure collisions with the CMS detector, as previously discussed, in ATLAS, which is what I work on, which is there. Now, when we measure collisions, one of the main particles we produce are quarks or gluons. And when you produce them, you actually get a very complicated image or picture of what's going on. They shower into more quarks and gluons. So sort of the red thing is what you produce first, and then you get more that come out of this, and those hadronize into stable or unstable particles. And the thing that you get at the end, this big collection of particles, is a jet. And jets are the things that we use to reconstruct quarks and gluons, and they're one of the more fundamental ways we measure things at the LHC. But when we measure a jet, we're not just measuring a single particle, but really hundreds per event. And mostly these are pions. And there's different kinds of pions that end up needing different kinds of calibration. And so our goal with this work is to identify, can we use the calorimeter and sort of the huge information we have in the calorimeter to figure out what the right kinds of calibrations are for each different kind of pion. So what do I mean about different kinds of pions and how are they different? Well, here's one way of visualizing this. This is one of the layers of our calorimeter in Atlas. On the left is a pi 0, so a neutral pion. On the right is a pi plus, so a charged pion. And so you can imagine that there's sort of 6 images like this behind this first one, because this is the first layer of our calorimeter. And the particles sort of would go out like from you and into the board. And so they deposit energy, and they have deposit energy with particular shapes. And so you could see on the left, the pi zeros look a little bit different than the pi pluses on the right. So if we treat each sort of energy deposit in each cell of a cluster, so this is sort of just a shower, energy shower from these particles, we can sort of start to look at this as a pixel intensity problem. So we could look at this as an image, and we can really try to understand from these simulated samples of pure pi pluses and pi zeros what they look like physically, what these, and whether we can extract information from this kind of representation. Right away, one thing you see is that pi pluses from this image, you might be able to just infer this, is that pi pluses are broader. They have a wider energy spread. This turns out to be very due to how they deposit energy in the calorimeter. It's a very different mechanism than pi zeros. And so this is part of one of the sort of mechanisms that we want to compensate for. They'll deposit energy differently because of things like this. So one of the first questions is, well, can you just tell the difference between these two types of pions? And it turns out you can. So here's a rock curve. It's a little bit different than some of the traditional formats. There's a pi plus efficiency on the x-axis. We're trying to identify charged pions, and we're trying to reject neutral pions, and that's on the y-axis. That's just 1 over efficiency. So we're comparing to a sort of baseline feature-based model, which is in these red dashes. And you can see this is just sort of a likelihood that's a two variable likelihood that was optimized a long time ago. It's sort of our baseline. And you can see with different types of neural networks, DNNs, CNNs that treat the problem like an image, where again, we're really scanning with the convolutions across the images and trying to identify features that are different between pi pluses and pi zeros. And then DenseNet, which is one of these industry standard classification CNNs. You can see that compared to the baseline, there's a huge performance improvement, which is a factor of 12 down in this bottom panel in the ratio you can see. So that's something that we are quite excited by. Another fun thing you can do is just try to see what the classifier is learning. And so what we do in these kinds of plots, on the left is the sort of, again, that first layer of the calorimeter. On the right is now the second layer of the calorimeter, so a little bit deeper into the calorimeter. What we do here is we calculate the correlation coefficient between each pixel and the classifier score. So you can really see how this is correlated with pi zeros or pi pluses. And in particular, you can see that the sort of center is always very correlated positively with pi zeros, and the energy on the outside in this image is correlated with pi pluses. And that's sort of what we expected from just like the physics intuition, but it's nice to see that the neural network can pick this up. So that's quite nice. And now the final question is, in terms of calibrations, what can we do? Because that's the fundamental question. So this plot is a little bit complicated. I'll walk you through it. On the x-axis is the true energy deposited by a particle. On the y-axis is what we call the response, which is the reconstructed over true. You just want this to be close to 1. And you can see compared to the green and sort of the red, these are the older feature-based techniques, what pi pluses look like. And you can see that they're not so great, but with the various DNN and CNN techniques that we developed, they get a lot better. So we see that the DNN outperforms the default, which is in the green, and this feature-based correction in the red. Similarly, for the resolution, this is again on the x-axis, sort of the true energy deposited. On the y-axis is basically the width of this energy deposit, how variant is that measurement. The goal is to get this to be close to 0. You can see once again, the blue DNN outperforms the other methods, especially the feature-based ones. So wrapping up, we have shown, I think, what's promising sort of results for charged and neutral pion classification and calibration with deep learning techniques. Better resolution can enable better physics at the LHC. And so we've seen that with the calorimeter, we really can do that sort of thing, which is really exciting. Much work remains, like comparing to data. This is all just in simulation. Further architecture optimization, integrating particle tracking, and then ultimately integrating this into the FPGAs for trigger applications. So thanks very much. And I have the links here, but I don't know if you'll be able to click that. But yeah, thank you.
Thanks, Max. So let's keep going. Mike Wang from Fermilab. So Mike, are you there?
Yeah, can you hear me?
Yep.
See my slides?
Yeah, go ahead.
Okay. So I'll be talking about using the GPU as a service approach to accelerate machine learning inference in neutrino experiments. So future neutrino experiments like DUNE will pose a series of big data challenge for neutrino computing. So DUNE, just to give you an idea of what it does, so it will investigate neutrino oscillations by sending a beam of neutrinos from Fermilab to South Dakota, where the neutrinos will be detected by 4 10-kiloton liquid argon TPC detectors 1.5 kilometers underneath the surface of the Earth. But in addition to beam neutrinos, DUNE will also search for signs of proton decay and also look for neutrinos from supernova explosions. So let's take a closer look at one liquid argon TPC module. So it has 384,000 channels total. And that means the readout rate for each module is over 1 terabyte per second. So for the entire detector, it's close to 5 terabytes per second. And so within 1 year, we're talking about exabytes of data. So DUNE's goal is to limit this to 30 petabytes per year. So this means we need to reduce it by 3 orders of magnitude. And this can be done with a traditional high-energy physics approach of using a hierarchical trigger architecture. For DUNE, the baseline trigger design is shown here. The input rate of 5 terabytes per second is reduced to 3 gigabytes per second. So even though 30 petabytes per year is a lot more manageable than exabytes per year, the increased use of deep learning algorithms in offline neutrino workflows can still prove to be a very serious bottleneck. So to investigate how we can solve this issue, we focus on ProtoDune, which is a scaled down version of DUNE. So here is a summary of the DUNE reconstruction workflow, which is very similar to that in DUNE. This is a simplified summary. So here you can see that the last step of the reconstruction workflow, which is a machine learning module algorithm used to classify a hit as either a shower-like, track-like, or Michel ID-like, takes over 60% of the entire workflow. So in order to address this, we adopted the GPU as a service approach, which abstracts the inference task as a web service. So in practical terms, we implemented the NVIDIA Triton inference server client within the LARSOF framework. LARSOF is a common set of tools used by all the liquid argon TPC-based neutrino experiments at Fermilab. And on the server side, we implemented the server in the Google Cloud platform by deploying a Triton inference server on a GKE cluster with 4 NVIDIA T4 GPUs. So here are the results. So we ran the reconstruction workflow on Fermigrid worker nodes, anywhere from 1 to several hundred simultaneous jobs. And here we plot the processing time for the machine learning module as a function of the number of simultaneous jobs. The two plots are essentially the same, except for the fact that the one on the left is with dynamic batching disabled, and the one on the right enabled. So dynamic batching is a feature of the NVIDIA Triton inference server, where it runs these algorithms to figure out what's the optimal batch size to use. And the different colored points are the different batch sizes that we initially requested. The orange line is a reference line of 220 seconds, which is the time it took to run the machine learning algorithm on a CPU. And the dotted lines are predictions of a simplified model, which is described in more detail in the longer talk. The thing to pay attention to is the saturation point on the right hand plot of 270 clients. So underneath, below this saturation point, the curve is essentially a flat line at around 13 seconds, which means that we have reduced the 220 seconds represented by the orange line by a factor of 17 times, which I think is pretty remarkable. And this translates to an overall speed up of 3 times for the workflow, the entire workflow. And the saturation point at 270 simultaneous clients means that one single GPU can serve up to 68 simultaneous clients with little or no impact to performance. So in conclusion, we have successfully demonstrated that the time-consuming inference tasks in neutrino workflows can be significantly accelerated with very little effort by offloading to an inference server like the NVIDIA Triton inference server, and thereby achieving remarkable speed-ups. So by doing so, we also get other benefits for free, such as the flexibility to easily update existing or introduce new machine learning algorithms as workflows change. You also have the flexibility of dynamically scaling the service in response to demand. You're also not tied to any particular type of hardware, since in principle, you can implement different types of hardware behind the server. So these last two benefits also imply that computing resources can be utilized in a more optimal way. So we are now currently in the process of doing tests at the production scale on ProtoDune data. So the work presented in this talk was a collaborative effort and is described in more detail in the following document. It is also part of a larger effort to promote the as-a-service approach in high-energy physics pioneered in the work described in the following publication. So thank you very much.
Thanks, Mike. And so now we go to our last talk, which is Ben from LBNL.
Great. Okay, so I will talk about the computational challenge of anomaly detection at the LHC, following suit with the rest of the talks from this session. So first, just briefly about the science. So the goal is to think about searches for new particles at the LHC, and schematically depicted here, where we collide protons, and if we have enough energy that goes into the collision, we can maybe produce efficiently some high mass particles that then decay into sprays of particles. The current search paradigm is typically 99% of searches at the LHC proceed as follows. You posit some well-motivated theory model, say supersymmetry, and then using that model, we build some feature space that's used to, some low-dimensional feature space to then construct some analysis strategy to find those particles. But the idea is, can we move beyond this current paradigm to relax the model assumptions and explore high-dimensional feature spaces in a more model-agnostic approach? And I like to think about model dependence sort of in this way. We need models to both achieve signal sensitivity as well as to calibrate our background. And focusing just on the left-hand side, there's a dependence on both the signal model that's used in the model that's posited to be the search target, as well as in the background model. And the background for us is the standard model. And there are a variety of searches that fill out this plane. Most searches, as I said, are rather signal model dependent and background model dependent. But there are a variety of other searches that relax these assumptions. And the kind of search I want to talk about today are sort of ideas that are signal model independent and background model independent as possible. So to just give you a little bit of a flavor, I'm going to focus on one particular search, although there are a variety of methods that are being proposed in this space. And the idea is goes by the name weak supervision. It's one flavor of approaches that uses less than supervised information to train. And very briefly, the idea is that imagine there's some feature that you know about in your feature space, high-dimensional feature space called MRes. And in that feature, the background is smooth, and if the signal exists, it's localized. You don't have to know where it's localized, but it's localized somewhere. Then basically you can construct regions that are, say, a signal region, which would be a narrow region in this MRes, and then a sideband region. And then all the other features in the data, shown here as this y dimension, can be used to basically, in a self-supervised way, develop an analysis selection that comes directly from the data itself. So basically to train a classifier that tries to identify small differences between the signal region and the sideband region in data. And so ahead of time, there's no specific analysis strategy. The strategy is sort of a meta strategy in that you say, I deploy this procedure to data, and then for each signal region, as you scan, say, from left to right, you develop a strategy that comes directly from the data. Okay, so I'm going to now show you very briefly some results to highlight that this method has been applied already to data. And the example will come from a dijet search. So this is a picture of the Atlas detector and transverse slice where the protons come into and out of the page. And you can see collision debris going transverse to that. So there are these sprays of particles that are called jets, as was introduced earlier. And the invariant mass of these two jets will be the resonant feature, because we know in a sort of a model agnostic way, if you have some particle decaying into jets, that the invariant mass of those jets will be the mass of the particle. So it'll be naturally localized. And then the substructure of these jets can be used to train this self-supervised classifier. And this has been deployed already in a very first pass by the Atlas experiment. And so here are the results. Just briefly, the results themselves aren't so relevant for this talk, but I just want to highlight that they exist and are competitive. So the y-axis here is the limit on the cross-section. So the lower the value, the stronger the cross-section limit. That means we say that there can't be any particles with that cross-section or higher. And then the values here in parentheses are parameters of the new physics. So the way that you set limits in this paradigm is that you take a signal and you inject it into the data and you see if you would have seen it, basically. Because as I said, the event selection itself depends on the data. So if you change the signal, you change the selection. And here there are 6 parameters. The various numbers correspond to masses of particles. And as I said, it doesn't really matter the details, but there's sort of an A particle decaying into a B and a C particle. And so you have the masses of all 3 particles. And the black points are the new limits, and then the red points and crosses are older limits, and the black ones are competitive, or in some cases much better than the old ones. But very briefly, I just want to say in the minute that I have left about the computational challenge. So as I mentioned, it's really a totally data-driven event selection, and so you need to train a lot of neural networks. So for every signal region, as we scan from left to right, there's some standard cross-validation that's done. This is done in part to use all the data. And then there's sort of some ensembling and over initializations and over test-trained val splits. And so this, for a given signal region, for one pass of the whole procedure, it takes like a few hundred neural networks. But this is embedded in a much larger procedure where basically, as I said, for every signal model, you have to rerun. And a signal model is specified not only by its parameters, but also by its cross-section. So every time you inject a signal model, for every cross-section of that signal model, and also in principle for every systematic uncertainty that would change what the phenomenology of that model would look like, you have to retrain a neural network. You have to embed this whole few hundred neural network scan. And so in total, you have to train something like 10,000 neural networks to make that plot I showed earlier. And this is where the computational challenge comes. And for this first round, the neural networks are relatively simple, but scaling up, this will be a big computational challenge. And so going forward, we're going to need much larger computing resources, in particular, possibly massive GPU resources that are fortunately available at HPCs. And this is sort of a very parallel procedure, but still we need a lot of compute power. So that's the end. I hope you'll see the rest of the talk, where I hope to convince you that deep learning-based anomaly detection has a great potential for discovery, and there can be a significant computational challenge to implement these in practice. Thanks.
Thanks, Ben. All right, so now we'll do like we've done in the other sessions, is that if you can post your questions on the chat, on the Zoom chat, and then we'll go from there. All right, go ahead.
Yeah, I have one question, Phil, for Ben, the last speaker. When you talk about the use of large GPU resources, are there any particular distributed workflows that you have been using in your community?
So I think that the way that this particular analysis is structured is very much embarrassingly parallelizable. So every entry of that loop you can make parallel, basically. And so it doesn't really matter where you have the computing resources. You don't need to run any fancy distributed training in the sense that you basically each of those trainings can be done on a single GPU, and then can be combined later in an ensembling way. Now it might be that in the future each neural network needs to be more fancy, but I think that the actual each individual training is relatively simple, and so it's more a matter of having many nodes and not so much how good those nodes are.
All right. So a follow-up then would be, maybe you heard about this effort by IceCube where they use over 50,000 GPUs for an analysis. Is that something that you would be pursuing, or it is more along the lines of HPC?
Well, I think they're not mutually incompatible. So for instance, there are HPCs that have a huge number of GPUs. So I think that strategy might be necessary going forward as we increase the feature size for this kind of analysis.
Thank you.
Thanks. Other questions? I'll ask a follow-up to Ben. So there are ways of embedding some of these systematic variations right into your network. I know you've thought about this a lot. So how would this either reduce the complexity or increase the complexity of the model? How does it impact the computing, let's say?
Yeah, so if you remember from my slides, I put the systematic uncertainties in parentheses. And that's one of the reasons, is that it might be possible to parameterize somehow. It's still a bit tricky because the data will change. Like, so if you change, the systematic uncertainties, the data will change, and then that changes everything. But I do think that can be parameterized, and I think that for small variations, especially because a lot of the nuisance parameters have really a small impact on the phase space, like the energy scale of your jets or something, that I suspect can really be done in a way that doesn't have a big overhead. There might be other variations that have a much bigger overhead, and certainly if you have like 1,000 variations, that is annoying because you just you have to really enhance the number of the amount of training data. But I do think that what you said is exactly spot on. That some of that should be able to be parameterized.
All right, I have a question for Max. So Max, you showed the single pion performance, right, and pi zero performance. But I was wondering, how much have you looked at like overlapping pions?
So that's a good question. We're definitely starting into that now. I would say that in general, the technique does seem to work. You might have to retrain it to account for the fact that you don't just get beautiful, perfectly separated pions. And in fact, this is a high occupancy, especially for high-frequency jets, you get a lot of overlapping things. So we are moving in that direction. This was sort of a proof of concept that the information is usable, and we do think that it will still work with higher density environments. And the other thing is, of course, if we incorporate tracking information, which we're also moving into now, there you also, because tracks are sort of finer grained bits of information, that'll also help in the higher density environment. So that additional tool should help us a lot.
Okay, thanks. Are there more questions?
I guess I have a question for Ben. So, you mentioned that to do Koala, you need to basically pick a variable that you think has a region of a bump in your signal or something like that. Have you thought about how you might do this, maybe with like an autoencoder where you say don't know, you think there is a bump somewhere, but you don't necessarily know what variable it is, or maybe it's a complex variable that you're not really capable of computing?
Yeah, that's very interesting. So a couple of comments. The first is that for a large class of models, you do know ahead of time where the resonance is going to be. Because I said, if you know that it's some object decaying into some other objects, then you kind of have a sense that invariant masses are really good. But you're absolutely right that there could be a class of models where you know that there could be a resonant object, but you just don't know exactly where it would be ahead of time. And we've thought a little bit about autoencoders. There is this really kind of nice idea proposed by some collaborators at Johns Hopkins, that does this, first does autoencoders and then does Koala, and then iterates the procedure. And that, I think, kind of goes in that direction. Basically, you use some other method to have a signal enriched setting, and then you use the Koala to basically use the supervision to really enhance. Because one of the challenges with autoencoders, just the whole full stack autoencoders, is that if you have an unsupervised method, it's not particularly sensitive to signal. It just says what's not background. And turns out not background could be very signal-like or could be very not signal-like. So it's kind of nice to combine that with some supervision. But I think this is exactly a very interesting topic for further research.
Cool, thanks.
All right, are there any more questions? All right, let me close on like an astroparticle physics question. So this is a question for Mike. There's interest, of course, to get the readout of neutrino detectors as fast as possible for supernova detection, especially at Dune. So I'm wondering how, like, given the rates we have now, how close are we to like real-time supernova detection?
Yeah, so for the, I'm not an expert here, especially there's so many other supernova experts here, but from the technical aspect, you just saw there's additional buffering in the upstream DAC for supernova readout. So I think the estimate is about 120, over 100 terabytes for supernova event. And they estimate that the fake rate for supernova is maybe about 1 per month. So it will be buffered for a while, and it will take a few. I mean, the problem is that it will take several hours to the disks or memory, wherever it's buffered, will be underground, and it takes several hours to transfer that to the surface, and then from there it has to be transferred to Fermilab. So we're now looking at ways to maybe speed that up, maybe do some of the processing while it's still underground. So.
Okay, thanks. I see Gautam, you have a question?
Yes, really quickly for Michael as well. So for optical experiments and even things like gravitational waves and experiments like IceCube, we get alerts whenever an event happens. And in particular, there's this group called the Scalable Cyber Infrastructure for Multi-Messenger Astrophysics, and Adam Brazier is here from there, that's been working on using this hopscotch system to send messages that say, we have found something interesting, into a queuing system. Is Dune using something similar? Can it be persuaded to use the same thing so that we can actually integrate all of this into a coherent multi-messenger follow-up capability?
Actually, that's an interesting question. In fact, I attended one of those, that workshop on this multi-messenger thing that you mentioned, but I personally don't know if the people in Dune are familiar with this yet, so I can reach out to them. So
that'd be lovely. Thank you so much.
Right.
All right, are there any questions? Any more questions? All right, let's close the session, and then we meet in, I guess, 10 minutes, 11:30 Central Time for our industry session. Thanks, and see you soon.